I'm going to speak to you today with this strange title, which I will explain. First, there is no proof, then there is. I'm talking about the birth of proof in the ancient Greek world, we should say. Probably Athens, but around Athens too, in the Greek world. And that is our main question. How did it come about? How did proof come about? We know that, as in a lot of history, not just mathematical, there are many anachronisms. Historians often tend to think of the past with the tools of the present or of another era. And there's been a lot of that in the history of mathematics. As many of you, Greek mathematics we know. People were talking about Greek algebra, Greek geometric algebra, Greek trigonometry, even Greek calculus. But that was just, if you look at the classics, Edward Heath's edition of Euclid, over 100 years ago, published, and still a classic. A lot of the language, the mathematical language there, is really much more modern. But that recent historians of mathematics, Reveal, Netz, Serafina Cuomo, and many others have broken that tradition happily and gone back to look at Greek mathematics as it was. Still, there is a strong anachronism in which we tend to think of Greek mathematical proof, say, as its prototype would be in Euclid, temporarily too, but also in terms of its huge fame, tend to look at it as an exercise in logic. Now, here's my title of my talk. The older folk among you may remember from the 60s the Donovan song. First there is a mountain, then there is no mountain, then there is. If you do, it comes from this quote by a 9th century great Chan, or Chinese for Zen master, who said, "Before I had studied Zen for 30 years, I saw mountains as mountains. When I arrived at a more intimate knowledge, I saw that mountains are not mountains. But now that I have got its very substance, I see mountains once again." So the trick here is to substitute proof for mountains. And for a long time, we tended to see Greek mathematical proof as logical. We must come to the point, and I hope we will in this lecture, of not seeing it as logical proof in whatever sense we identify logic in the context of modern logic, and only then can we see it properly as it is, or rather as it was, still is, which of course looks somewhat, I have to admit, like logical proof, but let me expand it. Okay, so the origin of Greek mathematics, the naive version goes back to Herodotus, who was not at all a naive man, and we don't know how reliable his information is, but according to Herodotus, mathematics came to Greece from Egypt by Thales, so that would mean around the beginning of the 6th century. We do know that Egyptian mathematics also probably was in interaction or had influences from one or two ways with Babylonian mathematics. But the thing is, if you look at what we know as Greek mathematics, again with Euclid as the paragon, the prototype, it doesn't look at all like the other kinds. So it makes us doubt a little bit what exactly it was that Thales brought, because say a typical piece of Egyptian mathematics, which you can look, this is from the Rhind papyrus in the British Museum, you can go and admire it there, it's beautiful, it's an equation, it's solving an equation in an algorithmic way, which is indeed very, very advanced, a lot before Greek mathematics, but is a very concrete numerical problem and an algorithm. Again, Babylonian mathematics, less concrete, more general statements, but if you look at it, it again refers to a rather concrete situation and gives you an algorithm for solving a numerical problem. But if you look at the theorem of Euclid, for example, it says that given two straight lines, constructed on a straight line and meeting in a point, they cannot be constructed on the same straight line and on the same side of it to other straight lines meeting in another point and equal to the former two respectively, namely each to that which has the same extremities with it. Now this is curious, curiouser and curiouser, as Lewis Carroll would say, since we want to remember logicians of the past today. And why is it curious compared to Babylonian or Egyptian mathematics? There are no numbers in it, they're just shapes. and there's nothing concrete or specific. What's most curious of all, if you look at the diagram of what it says, is that if you have these two segments, this one and this one, and they meet on this segment given, one starting here, the other there, and meet at point C, there's in fact only one triangle formed out of them. If there's another one, and that's in the proof, another one is constructed, and the proof goes proving that E is equal to C. Now, to a Babylonian or an Egyptian, if I may be a little anachronistic myself, I think that this proof would look not wrong, but so obvious or so irrelevant. And one would wonder why this truth, which does seem to be rather obvious if you think about it a bit and play around with the figures, would need a proof. But to Euclid it wasn't obvious at all because the proof is rather long. Okay? So, we shall focus the main question, which is where mathematics came from, and say what happened between the introduction to Greece of Egyptian Babylonian style mathematics around 500 BCE. So the classical theory of what happened in those centuries, very classical philologists especially, talking about what happened in Greece in the classical age, is that it was some sort of miracle. And that's why it was indeed called, until the end of the early 20th century, the Greek miracle. It didn't refer to mathematical proof specifically, but more generally to what was happening in Greece and in cultural life, philosophy, the theater, everything, and of course mathematics, big time. But like the gentleman suggests here, we should be a bit more explicit here in step 2, and that's what I'm trying to do now. Now, textual evidence. We're talking history. Of course, history is not just text, but it's a lot about text, and especially in an era when we cannot have interviews or what else. The only other thing that would help perhaps would be archaeology. Material artifacts are part of that. We can only apply reasoning. So let's look at what we've got first. The problem with Greek mathematics is that we've got absolutely nothing before Thales' time, 600. So we had nothing before Thales here. We have the first actual non-trivial proofs we have are of Euclid in 300 BCE. And we also have some full proofs, 330, but they're rather trivial. In fact, they're so trivial, if only they existed, we wouldn't be very impressed by what they prove. It's 2 textbooks on astronomy, which contain Euclidean-style proofs. Now, in the middle, we have 2 periods. The first, we have proofs, theorems, or other things referred to by later authors. X proved Y. Okay? And the second part of this period, we have works later quoted by later authors, and here the plural in works is a bit ambitious, very, very few. And there we have later authors telling us an older author of this period proved this theorem roughly this way. Now, Reville Netz, one of the great modern historians of ancient Greek mathematics, has said that the origin of Greek mathematics, including proof, could have been a sudden explosion of knowledge, and he places it even more concretely at around 430 BC, plus or minus 20 years. Now, the reason he says 430 and not 40 or 20 is because the basic evidence we have for a proof of that era, the strongest we have, is the proof of the squaring of the lunes, or half moons, you might say, the complements of the intersection of 2 circles, by Hippocrates of Chios, not to be confused with the doctor, and who was a merchant and mathematical amateur. But this proof we have from a 1st century Common Era book referring to a now lost late 4th century history of geometry quoting Hippocrates. So we have a 1st century author going 4 centuries back to another author going 1 century back and reporting what he thinks Hippocrates proved and how, and reconstructing the proof, but making a certain comment on what had happened in between, the ancient author. Now, from internalist evidence, we know proof developed over a period of some decades, and there's no footnote for the asterisk here, and the footnote. Internalist, for those of you not experts in the field, means from inside the mathematics, from inside the sources and fields of the history of mathematics, okay? So, from what we know of the texts, we have two styles, and that's declared by this first century author, which calls the way of that era of Hippocrates, 5th century, hypomnematikos, meaning, I would say, ed memoir. Hypomnema is a memo, a note to oneself. And that way was, its written form was just in cursory notes, really to be used as notes, as some of us may have notes when we make a speech and not a full written lecture, notes by the speaker to the speaker. The proof itself was communicated orally with a diagram, with a wax tablet probably. Around the speaker sat a circle of experts. There was an interactive process, Q&A, but why did you do this? Why did you draw this line? But what happens if that? And they are non-rigorous by our standards and by the standards of the 4th century non-extant author and the 1st century Common Era extant author. It's an older way, and in fact, when the 1st century author presents Hippocrates' proofs, he says, I cannot give it to you in that way, which is too primitive for our refined, eyes and ears, and I will update it a bit, and he makes it more Euclidean than it is. And then we have 4th century Euclid, and after Euclid we have written form of the theorem is complete. It should be complete in itself, prove the point in what you see written, fully understood when read, as a rule accompanied by a diagram, and rigorous, at least, by the standards that were considered rigor in mathematics until recently, or are still considered, except perhaps by logicians. Now, there's a problem here. Of this stuff, we have ample knowledge. We have hundreds of theorems of Euclid in full form, and hundreds of other theorems after him. Here we have very, very scant knowledge. In fact, I would say that apart from the book, the theorem of the proving of the squaring of the lunes by Hippocrates of Chios, we know very, 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 very little. So we have to create, to work in this area and set, because proof was born, this sudden explosion of knowledge that next places in this theorem, we have to do something else. We need externalist ideas. And externalist means from outside the field, because, Hippocrates of Chios was a merchant, after all. There was no profession of a mathematician as such. There was a profession of mathematician that was in fact the accountant, because Babylonian and Egyptian mathematics, and many people don't understand that, was very, very strong in ancient Greece, throughout Greece. And it was the mathematics of the accountants. There were hundreds or maybe thousands of them, mostly in Piraeus, where merchandise came in and out. But to go and look at Euclid-style mathematics, and Greek-style mathematics, let's call it, we need an idea from the culture at large and not just mathematics. I choose, like many people, to go in a way pioneered by two great French scholars in the 50s, 60s, and 70s, Vernon and Vidal-Naquet, who wrote nothing about mathematics, a bit about philosophy, but their central idea, which I will tell you about, was expanded and applied to philosophy and science, medicine mostly, some physics, but not mathematics, by the great Sir Geoffrey Lloyd, who is with us, and may God preserve him healthy and thriving and productive for many years. Now, the idea is this, of Vidal-Naquet and Vernon, that reason, logic, not in the sense of formal logic, but of logical thinking, had a lot to do with democracy, that it was the context of democracy that gave birth to the idea and the processes of logic, and as Geoffrey Lloyd expresses it, the style of demonstration owes something to the political legal settings of Greek adversarial culture I note here by demonstration he means not just in mathematics, in everything. The ambition is to find more than just hypotheses, but self-evident truths corresponding to an ambition to secure a demonstration that would silence the opposition once and for all. Okay? Sounds very vicious, but it's not. It's a huge progress, as Isocrates wrote about a century after the first mathematicians, because he says that through speech, through convincing one another by speech, through speech, and not, fisticuffs or swords or whatever, we created a civil society. Now, where did persuasion occur? It occurred big time in politics. It occurred in the theater, and the theater, I think, is particularly important because there it was as play, but also as experiment. Many of the ideas of the orators were played with in the theater, and this recent scholarship used to see, we were speaking of Euripides as a sophistical author, saying that he was influenced by the sophists, but there is now ample evidence that the sophists and the philosophers orators were influenced also by the theater and the form that dialogue and persuasion took in the theater. And of course, last but not least, and most pertinent to our case, we have the courtroom, and I'll focus on forensic speaking, where there are two fighting narratives, two accounts of a case, like today, like in courtroom dramas you watch on TV, and one tries to convince the jury of the other. So, a partial answer of the main question is that rhetoric happened, okay? But that is a partial answer, because rhetoric, as we know it, is not enough to expand and give us evidence for the genesis of mathematical proof. Before we do that, though, we have to drop genesis off. I don't like that metaphor of genesis. So I need a better metaphor, or one that is more suitable to the way I look at the problem. And this is a streetcar. You see its name is Desire. It is an actual streetcar named Desire. You all know the play. What you may not remember is that Blanche Dubois says in the play, I arrived here in a streetcar named Desire. And this streetcar actually existed. Why did it exist in New Orleans? This was its route, the route, and here there is Desire Street, and at first the line stopped at Desire. And so Desire meant it was the last stop, and the streetcar was called, in a sense, Desire. Now, but before and after, among the other stations, there was the final one end Canal, the other end France, and the first, before Desire, first the line went here, then to Desire, then to France. Now, what's interesting, and why I like this metaphor, is out of this quote I found, motormen could be induced to turn the crank and display an old route name so a tourist could snap a picture. With the popularity of the Tennessee Williams play streetcar named Desire, Desire was the most popular choice, but not the only one. The line was called at different times Canal, France, or Elysian Fields. Okay, so it could be a streetcar named Canal, which wouldn't sound as good. So the trick I do here is take this metaphor and put in poetry, storytelling, rhetoric, and proof. Proof, I mean here mathematical proof. When I say otherwise, I don't say otherwise, I mean mathematical proof. If you go left to right, is roughly, but time, not exactly. Poetry as in Homer. Storytelling as in quotidian storytelling, which we don't have oral, which goes back a lot, but also the historians in the 5th century, then rhetoric and mathematical proof, which comes after those. And so this is more or less historical. The way I look at proof is not as a genesis of, which means something coming out of something previously existing in full form, but I see it as a part of a streetcar route, which we could convince the driver to turn the crank and call it poetry, storytelling, rhetoric, proof. We have to widen our scope to understand what proof is. Now, other things were also happening, of course, in classical Greece, but logic comes as formalized by Aristotle a bit later. but they're not on that route, not exactly. Still, when we do get advanced forensic rhetoric, and we have very good examples of that in the second half of the 5th century by Lysias, Gorgias, and others, we have a convergence of storytelling, because they work with narratives, of poetry, you'll see why, because they use poetic techniques, and trial by jury, which is a cultural institution which necessitates it. By the way, those 4 things, poetry, storytelling, rhetoric, and proof, when they appear from now on in my lecture, they will be in blue, and the reason is not nationalistic, it's not because of the Greek flag, it's to remind you that they are referring to the root here. Okay? Agreed. Now, so what is the context of rhetoric in the 5th century? The givens are forensic rhetoric. 2 contrasting narratives, storytelling, 2 stories, which one was true, of what happened, a set of laws and principles, laws of the city, but also principles which are unwritten, by which the stories are judged. Which one is true and what law applies? What is wanted of the speakers, the 2 speakers, is a speech to enhance one's narrative and destroy the others, a secure persuasion at any cost, as Lloyd says, and a technique of rhetorical, not mathematical proof. This is not logical, no such thing yet, but based on the creative use of techniques of handling speech, mostly from poetry. One of the great orators of the time said that the aim of rhetoric was to make prose as beautiful as poetry. It was more complicated than that. It was to persuade, but it shows you something about what they thought. Now, the form was formalized in Aristotle, but don't believe Aristotle fully on the form. It's not always that. This is the perfect form, but it's good enough for our purposes. There is a prologue here, which sets out the aim. There's an epilogue which repeats more or less the claim. Sometimes it also has an exhortation and emotional appeal. There is the proof, which is what we talk about, and there is the narration. That's important in the forensic speech. What actually happened? So and so went there, so X, so Y, and murdered him, for example, says the prosecutor. Now, demonstrative techniques were taken from poetry, and I'm interested in those and studied those just because of my interest in understanding Euclid. I was going backwards on that route. So, the first is chiasmus, okay? We have a structure A, B, sentence B repeated either the same or similar or the exact opposite, and B star and A star. This is the most famous chiasmus that most modern people know, as not what your country can do for you, but what you can do for your country. You see the A is country, and the B is you, and B star and B and A star and A happen to be the same. They don't have to be, they can be similar or opposite, and of course that's John Fitzgerald Kennedy, not an ancient Greek. And also chiasmus can be longer, and sometimes is in Greek poetry. It can be very long. It can go A, B, C, D, E, F, F star, E star, D star, and so on. The longer one I found is in Homer. It's in the Nekia, in the ode where Ulysses descends to Hades and meets his mother. And of course, this is not Homer's words, it's my words, abbreviation. Homer, look at what happens. Look at 1. What killed you, asks Ulysses. The answer is the last, for his mother. So, a long sickness, Artemis, how is my father, how is my son? Has my wife been faithful? Your wife has been faithful, is the answer, the first answer. Your possessions are safe, which is asked in 6. Your son is thriving, asked in 5, and so on. So, the mother asks in reverse order. One of the reasons this could be happening, because the chiasmus, the extended chiasmus, is not a Greek invention, we also see it in Babylonian and other texts, is mnemotechnics. In oral delivery, it helps very much because memory is organized spatially, and we also know that. The Greeks knew that, and that's where the word topos comes from, because topos was a place where memories were stored as well as a space in the metaphorical use. But also we know that from neurophysiology now, that's organized spatially in the hippocampus of the brain, it was probably used by epic singers in order to be able to remember stuff better. Also because shorter chiasmuses had a pleasing melody, as it was almost musical. There was some secret harmony. Heraclitus says the unseen harmony is stronger than the seen. So there was this unseen harmony had a pleasing effect. And what happens in rhetoric is, the closest analogy I could find it was in biology. The term is exaptation, and here's the definition. Exaptation is the use of biological features originally evolved for other usages or for no function, and later co-opted for the current role. Stephen Jay Gould and Verba. The top evolutionary example is feathers. Feathers were invented, quote unquote, evolutionarily developed in nature as a mechanism to control as the temperature of the bird, going this, thus. And then, of course, were used for flight. But they were not originally created for that. And in our case, we have techniques used in poetry for aesthetic pleasure, for form, or as memory aids, later used in rhetoric when they proved useful for persuasion. An example, here is a short persuasive chiasmus as tool for arguing from contradiction. This is from Antiphon, the tetralogies, which are imaginary trials, two people speaking. So somebody says, nobody who was exposing his life to a grave risk, the malefactors, would forego the prize, the cloak of the victim, when it was within his grasp, and the victims were found wearing the cloaks. Therefore, the malefactors are not likely to have murdered him. It sounds very convincing, and it is a chiasmus, and it's the chiasmic form that makes it convincing. Here's another one from the Encomium of Helen, which is a longer one. Look at the center. It's an appeal to principle. Look at the center first, 3 star. For it is in the nature of things, not for the strong to be hindered by the weak, but for the weaker to be ruled by the stronger, which is chiastic in itself. And if you expand, you see 2 and 2 star, God is the word. And if you go 1 star, is who is responsible. And he argues that Helen is not responsible, it's the gods, using a longer chiasmus. And the second main technique taken from poetry is ring composition. And again, it can be longer. It can be A, B, C, B star, A star, etc., longer. And here we have a famous, again, my words, not Homer's. Long here, the central thing, as you see, is 9 lines in Homer, only 1 sentence here. This is the last ode of the last song of the Iliad, where Priamus goes to Achilles to appeal to him, to give him the body of Hector to bury. And while they're arguing about that very, very melancholy subject, Achilles says, let us eat now. Okay, let's stop and have a bit of lunch. So, and he says, let us eat. 1 line in the Iliad, for even, better expressed than here, for even Niobe ate. This was her story. Niobe, as you may or may not remember, had 14 children, and she offended Leto, saying she only had 2 and Niobe had 14. Leto got angry, had Apollo and Artemis kill them all, and Niobe was the archetype of the grieving mother, but at some point in her grief initially, in the myth, in some version of the myth, she ate. So Achilles repeats, she ate, so let us also eat. So there is a ring composition, and what Wilcock has shown in 1964 is that almost always in the Iliad, when a longer, older story, a myth, is used as a proof, as a guide to the present, it is in the form of a ring composition. Here is an interesting one. This is Thucydides, and don't be shocked, because Thucydides, like Euripides, is very sophisticated, very oratorical. So, this is the so-called archaeology, the first book of the history. It says, don't read the whole thing. Look at migration and emigres, beginning and end, best land and poor land, contrast in 2. In the beginning, there's a principle. Older authors, when they used principles or gnomon maxims, would use the received ones. Almost all the gnomon in Herodotus are proverbs, existing proverbs of the time. Almost all of the gnome in Thucydides are invented by him. So the gnome here, the principle is find land confers power, but this only attracts stasis, revolution, and invention. What I want you to note here is that unlike the previous ones, though migration is repeated, migration and emigre, the last line does not follow logically or is not logically antecedent or equivalent to the first. Migration was frequent because the defenseless were expelled by those larger, more powerful. Athens, Attica grew larger by attracting powerful emigrants and taking them in. And what's so interesting, you know, it's like the curious incident of the dog in the nighttime. What's so interesting is that it's not logical, and it shows you the extent to which chiasmus and recomposition had pervaded Greek thinking and Greek culture. Whenever you look, you see chiasmus and recomposition. They were habits of thought, and this shows it better than anything. And a persuasive recomposition too, as an appeal to facts. The facts are in the middle. It's a defense of Palamedes, imaginary defense as in Helen by Gorgias. The facts are no one could come to me, and I could not go to anyone, nor could the written message be sent. Those are already established previously in the speech. So if you look, 1, I did not commit treason, 1 star, I did not commit treasonable action, 2, no treasonable action, discussion occurs, 3 star, no discussion. Now, so we return to the main question, what happened? Rhetoric happened, but we have now to extend what we've learned from rhetoric to mathematical proof. But what is the prime suspect that makes rhetoric seem inapplicable to mathematical proof? Rhetoric is built on contrasting narratives, and in mathematics there are no narratives, at least as we think of mathematics today, or are there? Well, look at the scheme here, so that we saw that before. Look at the equivalent scheme formalized in later ancient authors of the Greek geometric theorem. There's a prothesis, a prologue setting out. Έκθεσης, διορισμός, κατασκευή, I'll tell you what those are. Then there's the apodixis, the proof. There's the συμπέρασμα, epilogue. Those look like rhetoric. So one could think that if there is something like a narrative, and we're looking for narrative, it will be here, okay? If the speech, if the model is rhetoric. So actually, the macrostructure of a theorem, the setting out, the έκθεση setting out, which is a triangle, let's say triangle ABC is the setting out. Specification is a triangle does this, C says triangle ABC does this. D, the construction is, you remember the diagram I showed you before with the two triangles, two possible triangles, is the construction of the alternative triangle. And so, in a sense, I will show you why this is a narrative world, this is a setting out of a narrative world, a concrete world of facts and events, and deconstruction is the narrative itself. So this would be like, the upper part would be like Middle Earth, and the lower part would be like the Lord of the Rings or the Hobbit. It's the environment and the story. And the proof uses narrative. Now, here I have a question for you. I'll take 3 very brief answers if there are any. What's the weirdest thing about Greek proofs? Greek proofs are weird in one particular way. Any very quick guesses, because we don't have much time?
We wrote them in the sand.
What? Drawn in the sand?
We wrote them in the sand.
Okay. Another one? You'll say aha when I show you something. There's something really weird in Euclid, for example. See, why is, when I learned that as a schoolboy, early back then we used to learn proofs, even in lower school in Greece, of Euclid. I said, sorry?
They're proof obvious things.
Not all of them. Some are extremely sophisticated. Extremely sophisticated.
We start from simplicity.
That's not weird. Yes, sir?
They use lengths instead of sort of integer numbers.
The young gentleman there is closer than all of you. Not exactly right. The answer is they're fetish for ruler and compass. You see, you say, aha. Everything has to be by ruler and compass. Why on earth? Why? I mean, why? At first, everybody just accepted, okay, that's the way the great Greeks did it, so fine, yes, ruler and compass. We didn't question that. Then, in the 19th century, there was Évariste Galois and some great proofs proving that some of the unsolvable problems, like the squaring of the circle by ruler and compass, were unsolvable for very deep reasons that had to do with algebraic and polynomial expressions. So some people thought that the Greeks were so wise, they knew everything about Galois theory. And they used those because they were the perfect tools for algebra. And that's anachronistic. So then there is no mountain, okay, then there's no mystery. And now we have to find the mountain again and wonder why. I knew why, compass and ruler, why. So that's what I did for some years. And I was looking at vases. Are there any Americans here? Vases. Okay, so, but because of the majority, I'll say vases. So this is from the 8th century, sir, from Cyprus, from your country. And if you look at it, there's something very, very moving. The first time I saw those things, I cried in museums. If you look here, you can see the pin in the middle. But that is not made by a compass. That was made by this instrument. A little wooden brush would stick with little brushes that they would stick in the vase in the wet clay and turn with ink. You cannot do mathematics with that. But if you look at 550, I asked 3 experts in archaeology on vases, of the greatest experts. When was the adjustable compass invented? None of them could answer it. You know why? Although they've been looking at vases all their life? For a very common reason in the history of science, because they weren't interested in it. They were looking at vases for the aesthetics, for the beauty, for the things. Here we see 2 circles, and if you look closer, I couldn't enlarge more, you see that the circles there are inscribed. They're not painted in the wet clay. And if you look at this painting, which is late 6th century, so around 500, you see something quite sophisticated, that the 2 shields intersect at exactly their centers. Okay, so that means you use the same distance and you work with that. Now, this is a breakthrough, the adjustable compass, which the archaeologists didn't know, but from my deep and profound archaeological researches, I'm joking, but I looked at thousands of vases, it doesn't appear earlier than 560 BC. Interestingly, it stops being used early in the 5th century, like 490, 480. Then vases become more aesthetic. They've played around with this thing. The fashion has passed, but it has left its mark. And the breakthrough for me when looking at vases was when I found a mistake. This is a mistake here. You can see very faintly a drawn figure under the handle of a small amphora. And it's a mistake because then the potter put black glaze over it to cover it because he didn't like it. But it can still be seen. Now, if you look at it, it looks like a daisy. He was trying to draw a flower. We see the same pattern on shields. I found one on shield. But look at this. This is a perfect hexagon. And this is an equilateral triangle. And it is an equilateral triangle created by compass alone with a given segment of given length. And that is exactly Euclid's proposition 1, 300 years later. The exact construction used by a potter is formalized 200 years later by Euclid. So what happened, I think, was rhetoric and extensive and sophisticated use of the adjustable compass. And to show you how extensive it was, 10% of the population of classical Athens was either directly involved in the vase-making industry, was the greatest export industry of Athens, or had relatives or close relatives involved in it. The adjustable compass was in every house. It was something everyone had seen and played with. So, though the usual, if I was a bit more classically inclined than I would say that when we move from rhetoric to proof, the other necessary thing is logic. But I give logic credit to Aristotle for the form in which we know it as formally, and go with vase painting. Now, how is that done? We don't forget rhetoric. Everything we learned in rhetoric is still there. But vase painting comes in with its compass, and we create with the compass also helps in the actions which make the narrative strong, because you can have descriptions and statements of general facts and so on, but without action you have no narrative. Look at this part of Euclidean proof. Description. BAC is the given linear angle. Like a story, the king is fat. Look at this. Then I join D with my ruler. Action. Now the king builds a castle. Look at this. Statement of fact. The angle BAC has been cut in half. The king is dead. And a general law. within the hollow crown that rounds the mortal temples of a king, keeps death his goal. That's referring to a proposition, using the method given in proposition 1.3, i.e. previously proven, are here functioning as absolute truth. And here's a mathematical chiasmus as a tool for arguing contradiction, taken from rhetoric, from 19 of book 1 of the Elements. As you see, every Euclidean theorem is chiastically constructed. Revealed Nets has noted this for 1, 2, 2 star, and 1. What we noted with my colleague Michalis Sialaros is that almost every, we didn't look at all of them, frankly. He may be doing so because he's editing Euclid anew, but I looked are complex interplay of chiasmus and ring composition. Here, look at the proving chiasmus. In fact, AC is not equal to B. For them, angle ABC would also have been equal to ACB, but it is not. 5 star because it negates 5. And then 4 is just a pure repetition, 4 star of 4. Why does he repeat it? Unless he's working with the chiasmus. A modern mathematician would eliminate, would stop at 5 star. And a mathematical ring composition, just one example for appeal to principle. This is our old friend, if you remember, the equilateral triangle we saw constructed 2 centuries earlier in the vase. And if you look at the central ring composition, but CA was also shown to be equal to B, thus CA and CB are each equal to AB. 5 is common notion 1 in Euclid, but things equal to the same thing are also equal to one another. Thus CA is also equal to CB. So you see CA and CB in the second line of 4, and you see them again there. So it is that, as in Homer, that you appeal to the principle. In Homer, the appeal to principle was a myth, but here the principle is a general statement. So Greek proofs are a subgenre of rhetoric, really. The aim is persuasion, as in all rhetoric, but in this case, to persuade, silence the opposition once and for all, an audience of experts in geometry, and not, the jury or the citizens. They are action, i.e. narrative-based. They use rhetorical techniques to argue about the rightness of a geometrical narrative, often introducing a counter-narrative, that's the reductio ad absurdum, like in the 2 triangles, the 2 positive triangles, a counter-narrative which they destroy. Their main tools of bricolage are X, which I use for chiasmus, and RC for ring composition. And they contain no syllogisms, which comes as a shock to many logicians. If you go through the whole of Euclid, there are very, 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 very few syllogisms. What you have is empty meanings, which are truncated syllogisms and used by orators. And what about modern proofs? And I finish with this. Let's take a very famous proof, Andrew Wilde's proof of Fermat's last theorem, random paragraph. You don't have to understand any of the language. I don't, but I look at the words. Statement of fact. To change from an Omicron algebra to an Omicron 1 algebra is straightforward. Fact, obviously. Can't you see? Action. Now, the king builds a castle. To change from Selmer something to order something, we use this. Description. The R is a local Noetherian ring. And, of course, general law, 1-4. Again, as in Euclid, we know this because we proved it earlier. Now, this work was presented mostly in 2 papers, one written by, authored by my friend Michalis Sialaros, young historian of mathematics, and myself, and the other by myself, and they appear in those 2 books. If you want the references later, I can give them to you, and thank you very much. Thank you.